equations and inequalities is another topic we need in order to describe other kinds of ranges, but most importantly, what the definition stands for, So maybe for practical purposes, every time you see that absolute value bar in the math notation, all you do in the end is to whatever number you have inside, whether it's positive or negative, it's going to be the same number, just change it to a positive. Absolute value of negative 3 is positive 3. Absolute value of negative 7 is positive 7. Absolute value of 1 is positive 1. So regardless of what you have inside, it's always positive. All right. However, it is the definition what we really need to have an understanding of what it is, because again, that's going to come back later when we describe certain ideas in trigonometry. So number one, absolute value. The absolute value of a number A, which is denoted with these vertical bars around, is the distance from 0 to a real number. So that's why the result is always positive, because, for example, if this is 0 right here, I'm going to go 1, 2, 3 steps, right? I'm moving to the right 3 steps. Even if I move to the left, that's 1, 2, 3 steps, right? But I'm not moving negative 3 steps. I'm still moving a positive number of steps. However, it is the sense of direction what actually makes it positive in this case. And for instance, we have this this visual example right here. So the distance from 0 to 3 on a real number line is 3 units. It's 3 units. So the absolute value of 3, which is in this case, absolute value of 3 equals to 3. And likewise, the distance from 0 to negative 3 on a real number line, which is denoted absolute value of negative 3, that equals to also positive 3, because again, it's the number of steps that we do. So from 0, for instance, I'm going to use the 0 as a reference. So I'm going to go to 3. That means it takes 3 units. All right? And even if we go in the opposite direction, that's also 3 units. 4 steps again. So when you're going north, say you go 5 miles towards the north, so the fact that you go 5 miles towards the south, you don't say I'm going to go negative 5 miles, right? You go 5 miles, but you indicate a direction, right? So actually these positive or negative values are going to come later, almost at the end of the semester, when we look at vectors, which indicate not only a magnitude but also a direction. And this applies to forces, velocity, that will be modeled with certain mathematical models. But again, we're going to get into that a lot later in the semester. In the meantime, let's look at absolute value equation. So now, consider the equation absolute value of x equals to 4. So what is this equation asking us for? All right, this equation is asking for which real numbers x are 4 units away from 0 on the number line. All right? And well, what are those two numbers? Negative 4 and positive 4. All right? So all the numbers that are 4 units away from 0, well, that's our reference. And also negative 4. And again, even though we go towards the negative side, that's because the number of steps, and there is no such thing as negative steps. No, it's still positive steps. It's just going in the negative directions, right? That's 4 units. And also 4 units. All right? Now let's see, what are the steps that we follow to solve absolute value equations. And that's something you may have seen before. So in high school, they might have told you, oh, you solve absolute value equations. All you do is get rid of the absolute value bars, write the expression inside the absolute value bars equals to the positive value on the right, or equal to the negative value on the right. So you write two equations, but again, the reason why we do that, what we really care, the fact that we're looking for the values that are not 8 units away from 0 in this case. All right? And this is what we do. We rewrite the absolute value equations as two equations. That's the most important part. We solve individual equations, and then sometimes we are required to verify the solution, not all the times. And that's just in the cases in which we get like quadratics or other ones that contain radicals, but we're not going to go through those kinds of equations. We're just going to limit to linear linear absolute value equations. Well, so let's solve each equation right here. So let me do one and then I'll let you work on the next one. So we have an absolute value equation. So the first thing we do is isolate the absolute value term. And in this case, notice nothing is multiplying the absolute value term and nothing is extra or dividing the absolute value term. So we're ready to break this up into two separate equations. Number one, we're going to write this x minus 2 equals to negative 3, or x minus 2 equals to 3. Again, let me highlight this. Negative 3 and 3. So we're doing the negative a and the positive a, just so you can see what we're doing here. And now what we're going to do here is solve these two baby equations. I mean, we need only one step to solve each of them. That is, add 2 to both sides. And that's going to leave us with x 2 minus 3, that equals to negative 1. All right? And lastly, for the second equation, let's see, we add the 2 to both sides, and that's going to leave us with x equals to 5. All right? Now, I would like to extend this concept a little bit. Okay, so here is the thing. Let me go back to the definition right here, to the definition in the previous step. All right? So if we were a little more strict about the notation, well, here this equation I gave you about x, absolute value of x equals to 4, which asks which real numbers are 4 units away from 0. So this absolute value represents the distance, which is 4, which is the number on the right hand side. But again, keep in mind that every time we're looking for distance, what do? We subtract the location from the furthest place minus the location from that is to the closer place, and that's going to give us the difference, the distance between the two. We don't do it the other way around, because we do it the way around, we will get a negative value, and even though it's the same number, it's not practical to work with negative distances or the like. So what I'm trying to say, okay, let me restate this equation right here. Absolute value of x, but do we agree that x is the same as saying x minus 0? I mean, I know, it's like, why do I put that 0 in there? Because distance from any number x and 0. All right? That's what this term on the left-hand side represents. This absolute value is the difference, it's a distance between x and 0. All right. Now, how about we apply this same idea to interpret what the first exercise did for us? Okay? Let's go for it. So, well, let me give you a few more seconds if some of you are still writing it. All right? All right. Okay. So now, for this exercise, okay, the equation x minus 2, absolute value of x minus 2 equals to 3 is asking which numbers x are 3 units away from, not from 0 this time, but in this case from 2. All right? Be careful, not from -2. The negative is just to subtract that value in order to help us find the difference, which is the distance, right? So if we express this using a number line, that's going to give us, okay, let me put the 0 in the middle for reference. And then I'm going to go to the number 2 this time. That's going to be our center, if we will. Okay, so that's a 2. And then from there, I'm going to go 3 units in each direction. That's going to be 1, 2. Well, let me use a different color for this. So that's going to be 1, 2, and 3. All right, that's going to be 2 plus 3. Isn't that equal to 5? And I'm going to go 3 units in the opposite direction. 1, 2, and 3. And that's going to end up in the number -1. Are those numbers in yellow the same two solutions from solving the absolute value equations right here? So in the end, that's what it represents. So we're looking for the numbers that are, in this case, 3 units away from the number 2. So that's the real meaning behind solving an equation like this. All right. And by the way, every time you're given an absolute value equation, all you have to do is you don't have to do the interpretation. This interpretation here, I'm just doing it so you can see the reasoning behind or rather, yeah, the reasoning and the real meaning behind solving an it's not an inequality, an absolute value equation. Yes?
Just to clarify, we're going 3 units away from 2 because 3 was the solution.
Because it's equal to 3, because it's the distance between any number and 2 to be equal to 3. I mean, yes.
Because we got 3 and -3, so
exactly.
It's going to be 3
Mm-hmm.
from
So,
whatever the number that it just so happens to be 2.
Exactly, which is what this plus and minus represents. The plus represents to go towards the right, while the minus represents to go towards the left. Right? So let's see, let's look at letter B. So the difference between exercise A and B is that, well, exercise A was just given in a way that was ready to just split it into 2 equations because we already have that absolute value term by itself. Here, we don't have that absolute value term. So for now, first let's subtract the 3 on both sides. And well, that's going to leave us with absolute value of 3x minus 2 equals to 10 minus 3, which is 7. It is from here that we break it up into 2 equations. No, we don't add the 2 to both sides because we have this expression in a way protected by the absolute value bar. So the minute you see this form right here, that's where you write when you write it in terms of 2 equations. That is, well, on the one hand, 3x minus 2 equal to the -7. Well, I always write the negative first and then the positive, but it doesn't matter if you want to do the positive first and then the negative. Either way, it should work. All right. In the end, we're going to write a list of solutions, not only one solution. So, and then 3x minus 2 equals to +7. All right. So let me highlight so you can see how we get to write it equal to the negative part and then equal to the positive counterpart. Here is where we now solve each baby equation here. That is, add 2 to both sides. And on both equations, if you want to do the 2 at a time, or just the one at a time, that's fine. That's 3x equals to negative 7 plus 2, that equals to negative 5. And divide both sides by 3. And that's going to leave us with x equals to negative 5/3. Alright, and preferably we leave them in fractions. And make sure to leave fractions reduced to lowest term. Well, this one is reduced to the lowest term. Because my math lab, when you're doing the homework, most of the times, well, this system is very picky if you don't write, or if you don't input a fraction that is reduced to the lowest term. It's going to give you a notification that says, although your answer is correct, it's not reduced to the lowest term. So they're just asking you to go the extra mile. And then over here, that's a 3x equals to 9. And then divide both sides by 3. And that equals to x equals to 3. So two solutions. And these are the two solutions that we will input on MyMathLab, separated by comma. Well, you'll see the instructions in the program when you get to it, right? Yes, okay. So we get this after subtracting 7 to both sides, we get this absolute value to x plus 5 equals to negative 4. However, think about this statement right here. And think whether that's a real meaning, actually. I mean, I know that the steps after isolating the absolute value term is to break it up into two equations, one with the opposite sign of this number and one with the same sign, right? However, I mean, yes, you obtain two results potentially. However, think of the definition of absolute value. It doesn't matter what you have in here, the 2x plus 5, but I mean the real meaning of absolute value. Isn't that the distance between a number and x? Right? However, can we have negative distances?
Yes.
No. So again, we can move 3 units to the right or 3 units to the left, but with the fact that we move 3 units to the left, that doesn't mean we're moving 3 units, or rather negative 3 units. So in this case, no solution. Right? Since distances cannot be negative. All right? Distances cannot be negative. All right? So you might want to be extra careful with that kind of exercise, all right? Something that can potentially be on the quiz next time, all right? Now let's see. All right, so let's look at the next topic, equations involving two absolute values. Well, more often than not, you may get to see equations containing absolute values on both sides of the given equation. Well, don't let that freak you out. Just write one positive and one negative. That's all we do, as if we had the right-hand side not containing variables, just a pure number. That's fine, and that's good enough. So again, and you want to highlight this part. This is every time we got the absolute value of u equals the absolute value of v, do one with v positive or one with v negative. All right? And how about we look at one example here? So let's see. So this breaks up into two mini equations. One with a 2x minus 3 equals to negative the quantity x plus 6. And another one, okay, make more room. And another one with a 2x minus 3 equals to the positive x plus 6. And let's solve each individual equation. Number one, let's distribute the negative over the two terms inside parentheses. That's going to give us, well, that's just going to change the sign, right? So that'll be 2x minus 3 equals to negative x minus 6. And then again, recall that to solve equations, move over all the variables to the left and all the constant values to the right. That is to get, okay, that's add x to both sides, and 3x minus 3 equals to, cancel these two, equals to negative 6. And then from here, let's solve the linear equation, add 3 to both sides, and then get rid of the other 3 by dividing both sides by 3. So add 3 to both sides. And, whoops, didn't go through. Okay, cancel, cancel. That's 3x equals to negative 3. And then divide both sides by by positive 3 rather, not negative. And that's going to leave us with x equals to negative 1. So that's one solution. Now we need to solve the second equation, because again, this is going to give rise to two separate equations. So in this case, let's subtract x from both sides. That's going to leave us with 2x minus x, that equals to x minus 3 equals to 6. And then add the 3 to both sides. Well, that's a shorter equation. That's equal to x equals to, what's that, 9, right? So in this case, again, two solutions. And well, so here, and just to give you a quick summary of absolute value equations, well, we would be getting, for the most part, two solutions, because again, if you stand at a point, there's two places where you can go about the same number of steps to the right and to the left. So that's why we get a total of two solutions. All right. All right, let's have a look at this one. Well, so again, solving an absolute value equation involving double absolute values, it's the equivalent to solve two equations. Number one, x plus 1 without the absolute value bars, and the right-hand side to x plus 3, however, with a negative in the very front. That negative affects both the 2x and the 3. I noticed some of you put a negative but only put it for the 2x, or even if you put the parentheses, forgot to distribute the negative for the 3. So you need to be careful there. So that's 1, that's 2, that's x plus 1 equals to 2x plus 3. So let's distribute the negative. That's x plus 1 equals to negative 2x minus 3. And then, well, again, x is to the left-hand side, constant values to the right. So add the 2x to both sides to get 3x plus 1 equals to negative 3. And then keep the process, subtract 1 from both sides. That's going to leave us with 3x equals to negative 4, and dividing both sides by 3, that's a negative 4 thirds, which is what most of you got for this one, right? All right, let's see. Let's look at the second equation. This one is going to be a lot shorter, so that's subtract 1 first, if you want. That's x equals to 2x plus 2, and then subtract 2x. That's going to be negative x equals to 2, and simply divide by negative 1 on both sides. That's because, well, you don't want negative x, you want x in this case. So x equals to negative 2. All right? Two solutions. Absolute value equation is two solutions. All right, so let's see. So a couple of examples, right, on solving absolute value equations involving two absolute value terms on it. All right, let's see. So let's move on to the next topic. So now let's solve inequalities. Inequalities like the ones we solved before in the previous review packet. However, we're going to at this absolute value? Well, of course, again, we're going to look at the meaning of solving an absolute value inequality, because again, you may have solved this kind of inequalities before. However, well, maybe you didn't get to see what the real meaning is to solve them, right? And well, let's consider a very simple case right here. All right. So the inequality absolute value of x less than 4. Okay, so this inequality is asking which real numbers x are less than 4 units away from 0 on the number line, right? So that's what the answer that we want to answer here. I mean, the question that we want to answer. All right, let's see. So let's go to 0 first of all. And then from there, what numbers are less than 4 units from 0?
So you do parentheses, -4 and +4.
All right. Okay. So let's test some numbers here. What about +1? Is that number 4 units or less than 0, or 4 units or less away from 0? What about 2? It's also 4 units or less away from 0. What about 3? It's or not 4 units, or just less than 4 units. Never mind. Okay. What about 3.5? What about 3.9? What about 4 itself? Is that less than 4 units? Oh, here is where we exclude the endpoint, right? So that's going to be, like Corey just said, we put parentheses here, right? Now let's go with the opposite direction. So what about -1? Is -1 less than 4 units away from 0? What about -2? What about -3? What about exactly -4? But what about any number like -3.999, -3.99999? Well, so we represent that using parentheses. So essentially, we're not just looking for two values like in the equation. The equation is exactly 4 units away from 0. Exactly 4 units away from 0. Just two numbers, two values. Here, it's a set of many, many values. And well, where have we seen this before? Didn't we see anything like this in the previous compound inequalities? All right. So here is the steps to solve an inequality, to solve absolute value inequalities involving the less than or the less than or equal. So solving the absolute value of u, where u is an algebraic expression like 3x plus 5, 5x minus 7, you name it. So this one, absolute value of u, is the equivalent of solving this three-sided inequality like the one we saw at the very last of the previous handout, And then, well, solving the absolute value, but in this case, including having the less than or equal, that actually changes the inequality symbols for less than or equal. So, and again, to connect these ideas, so to solve this type of absolute value inequalities, that's the equivalent of solving and inequalities the type 2 as in the previous section, in the previous review section. All right? So let's see. Let's look at one example, well, actually a few examples of this. So, and we need to be very careful. These remarks right here. So whenever we have an inequality, an absolute value inequality, so absolute value less than 0 has no solution. Okay, let's highlight this. This is very important, and let's discuss about why is that true. All right. Okay, so any ideas why that inequality has no solution? Corey?
Because it is excluding 0, so there's nothing less than 0 that isn't 0, if that makes sense. Or you can't have it without the equal to, essentially. It's the only value that would be present in that space. Would be 0, so
Okay, well, again, let's keep in mind that this absolute value represents distance. Okay, you have a distance, a distance value that is less than 0. So what are the numbers that are less than 0 to begin with? Negatives, right? So can we have negative distances? So that's why the minute you see an inequality with a 0 on the right hand side with less than, then there is no solution. However, be careful with the other case, the one that has the less than or equal, and that is the equivalent to just solve the u equals to 0. Okay, let's break this down and explain why is that. Well, so here, whenever we have absolute value of u equals to, or rather, less than or equal to 0, this means two things. Either we do the absolute value of u less than 0 or the absolute value of u equal to 0. We already saw that or discussed that we cannot solve, there is no solution for that. So really, the only alternative is to take the absolute value and solve it for equal to 0. However, absolute value equal to 0, would it make sense to write it like u equals to negative 0 and u equals to 0? There's no such thing as negative 0. That's why we just go with the u equals to 0 case. Right? Let's look at some examples to see this in action. Okay, solve the following absolute value inequalities. And well, even though the instructions don't state it, we're going to write the results using both set notation and interval notation. All right? So, now, again, okay, let me have this one here. Looks like this exercise in particular looks a lot like the generic case that is highlighted in blue. So that's why I'm going to highlight it in blue. Okay, so this is what we're going to do. I'm going to rewrite the exact same inequality here. That is 3x minus 9 without the bars, without the absolute value bars, set it less than or equal to 6. And also greater than or equal than negative 6. All right? And then, well, you know how to solve the kind of inequalities, right? Add the 9 to the 3 sides and then divide by 3 on the 3 sides to get, because our goal is to get the x in the very middle. All right, so let's see. Add the 9 on the 3 sides. Cancel these two. And that's a 3x less than or equal 6 plus 9, which is 15, and negative 6 plus 9, that's a positive 3. All right? And lastly, just divide by both the 3 sides, and not both sides, the 3 sides by 3. Over here, all the 3's get canceled. And that's going to be 1 less than or equal to x less than or equal 15 divided by 3, which equals to 5. And that's our solution. Again, this process we just did over here should look familiar from what we did in the previous handout. All right? So now, again, we need to write this solution set using both set builder notation and interval notation. So the result we get out of solving this inequality, which is a compound inequality simplified for x, this is just ready to copy and paste it into curly brace to represent the set builder notation. So that's x such that, and just write it down, 1 less than or equal to x less than or equal to 5. Using interval notation, that's between 1 and 5, but including the endpoints. And the reason why we include that is represented by brackets, that's because we had the less than or equal. Right? And that's one example of how we solve these absolute value equations and inequalities. Again, these are going to come later when we look at some situations in which this idea, this powerful tool is required to solve certain problems in trigonometry. You'll see. All right? All right, let's have a look at this one. Let's see. So what do we have? The absolute value 5x plus 8 minus 12 less than 4. So notice this, in this case, we don't have the absolute value term by itself. So first we need to isolate it. That is by adding the 12 to both sides. That's going to give us the following inequality. That is 5x plus 8, absolute value of that less than 16. So now we may go ahead and get rid of those absolute value bars like this. 5x plus 8 less than 16, but make sure to also make it greater than its counterpart, negative 16. All right? So, and then from here, just solve the three-sided inequality. That is, subtract the 8 on both sides. That's going to give us a negative 24, less than or less than only 5x, less than 16 minus 8. Is that 4? No, it's 8 actually. And then divide both sides by 5. And that's pretty much it. There's not much else to do. Negative 24 fifths less than x less than 8 fifths. And then, well, from here, let's use this inequality to write a set builder notation for this. That is x such that negative 24 over 5 less than x less than 8 fifths. And using interval notation, as we did in day 1, in which we just wrote the endpoints of the interval with the corresponding grouping symbols. All right, that's a negative 24 fifths less than, to 8 fifths. All right? And I did a mistake on purpose to see if you can catch what I did wrong. What did I do wrong?
The brackets.
The brackets, right? They should be parentheses, right? That's because we don't have the equal part right here. All right? All right. Let's look at number 3. All right, number 3, and again, make sure to leave that absolute value bar or absolute value expression by itself. And again, let's subtract the 12 on both sides. That's going to give us the following: absolute value of 5x plus 8 less than negative 8. Now, let's talk about this statement right here. What about it? No solution. Ladi, what was your input here? But why is that a no solution? Because, and what is that negative 8 representing? So, okay, can we have a distance that is less than a negative number, than already a negative number? That's weird. So, no solution. All right, and actually this is described over here, right here. I have the less than 0 case only, but I mean, that works for every other number, less than 0, less than -1, less than -2, less than pretty much every kind of negative number here. All right. Okay, so let's see. Let's have a look at the absolute value inequalities, but this time involving the reverse inequalities, the inequality symbol, that is greater than or equal. Now, in a similar way that we did before, we are going to consider this very simple inequality. All absolute value of x greater than 4. This time this inequality is asking which real numbers x are more than 4 units away from 0 on the number line. All right? Okay. Let's start at 0 as our reference, and let's count units. Okay, I'm going to go to the number 1. Is 1 more than 4 units away from 0? What about 2? What about 3? What about 4? Not 4, but what about, well, that's because we don't have the equal part. But what about 4.000001? Okay, so to represent that, it's going to be, we're going to use parentheses, and now we're going to keep going. How about 4.5, 5, 6, 7, 25, of course, right? All the numbers towards the right of 4, excluding the 4. And let me shade this using this, shading that interval of values. Okay, let's do the same, but the other way around. Recall that distances can go in one direction and in the other direction. All right, and although for now we're just limiting to go about only one single variable, one single direction, left or right. Later in future courses, when you get to multivariable calculus, you're going to see this again, but not just going into x direction, positive x and negative x. You're going to see this also including the y, the positive y, negative y. Actually, that forms a disk. And you can get to the 0 using many different paths. But well, let's leave that for later. All right. Now let me go about the other direction. Is -1 more than 4 units away from 0? Now what about -2? -3? -4 itself? But well, we're going to start from there, right? And then like this, right? And that's going to be our solution. Now, where we have seen these kind of solutions to inequalities, remember from last time when we solved the OR inequalities? Well, that's what we are going to be relying on. All right, so let me do the same kind of highlighting as the same way we did it before. So this one right here, which looks pretty much like the one that we just solved right here, because for example, absolute value greater than a is equivalent to solve u less than -a or u greater than a. And well, to be more explicit about the previous example, well, what we have here, absolute value of x greater than 4. So one possibility is to go u, which in this case x less than -a, which is -4, or u greater than a, which in this case a is 4. All right. And well, we can see, oh, not u, it's actually x. Should be x in here. All right. And these shaded sets right here are represented by x less than -4 and x greater than 4, as we've seen before. All right. So how about we see this in action with more elaborate examples? Oh, before discussing that part, before discussing the examples, of course we have the other case in which we have the equal part. There's not much different other than the inequality symbol that we're going to use this time. All right? Okay, so the equivalent, again, of solving this kind of inequalities is to solving the OR inequalities from the review handout we did last time. All right, let's see. So solve the following absolute value inequalities. So number 1. So in this case, we already had that absolute value expression by itself, isolated. Now we need to, number 1, okay, we can go ahead towards the right and write 2x minus 5 greater than 3. Okay, so we just get rid of the absolute value bars and write it on the one side. On the other side, I'm going to write the 2x minus 5. But in this case, flip the inequality symbol and change the sign of the number 3. So that's going to be an OR kind of problem. And again, the OR is going to look for only the union, the union of the set, as opposed to the intersection, which is the and type of inequality. All right, let's solve these two baby inequalities for x. So add 5 to both sides. Oh, use different color. Add 5. That's 2x less than 5 minus 3. That's positive 2. And then x, divide both sides by 2. And that's x equal, not equal actually, less than 1. And that's the solution to our first inequality here. Now let's solve the second inequality. Let's have about, also add the 5 to both sides. And that's going to be the 2x greater than 5 plus 3 equals to 8. And divide both sides by 2. And then x greater than 8 over 2, that equals to 4. Now, here is what we're going to do. Call this set A and call this set B. In the same way we did it in the previous review section, in which we combined this kind of inequalities, the over inequalities. And again, we're going to do a number line to represent set A, and another number line to represent the set B, and then put the two together as a sandwich. The same way, in the same way. All right. So that's set A, set B, and in this case, A union B, right? A or B. All right. So let's see. Again, have the zeros in the middle for reference to have a good number sense. And then, well, let's go to the number 1, and because it's a less than, that means we're going to go all the numbers that are to the left of 1. Okay, so I'm going to go 1 to the left, and let's shade using blue. I'm going to go, what's next? 4. 1, 2, 3, 4. But this case to the right, because this greater than indicates towards the right like an arrow, or all the numbers that are greater than 5 are actually to the right of 4. All right, so let's see. And putting the two together, well, into one single set, well, we're going to get the following: 1, 2, 3, 4, like this, like that. That is the blue one and the pink one. All right? And well, again, in this case, we are looking for the union of the two sets. That is, the elements that are in either A or B or on both. But in this case, there's no overlaps between the two. If there were overlaps, it could have been potentially the whole real number line, like that first example we did last time when we were looking at the different cases for sets, to shade sets. So in this case, I will represent this, this first interval coming from negative infinity, stopping at 0, but we exclude the 0 using parentheses, and then that gap in between where we don't have anything shaded, we will have a union symbol. And then represent the interval in pink. I meant 1, right? Yes. And then that's going to be 1, 2, 3, 4 to infinity. And that's our solution using interval notation. But of course, we also have to represent this using set vector notation. Well, all we do here is open curly braces, x such that, and write these two inequalities, x less than 1, comma, x greater than 4. And that's about it, right? That's about it. All right, so number 2, solve for x, absolute value for x plus 3 greater than minus 8 and greater than negative 3. So first of all, make sure to add the 8 to both sides, that is to isolate the absolute value term, that is 4x plus 3 under the absolute values, the absolute value bars, and 8 minus 3, that equals to 5. And then from here, we're good to go. We're good to break it up into two inequalities, that is 4x plus 3, exactly the same format, greater than or equal to 5. However, no more absolute value bars this time. And then, that is 4x plus 3 less than 5, less than or equal 5, but in this case with the opposite sign. All right. So let's solve each individual inequality and see what we get. So let's subtract the 3 from both sides to get 4x less than or equal negative 5 minus 3. That's going to give us negative 8. And then divide both sides by 4. So x is less than or equal to, that's going to be negative 2. Right? So that's the result for our first inequality. Now let's solve the other inequality, which is, well, it's again, subtract rather the 3 on both sides, and that's a 4x greater than or equal to 5 minus 3, that equals to 2, and then divide both sides by 4. And that's x greater than 1 or equal to 1/2. All right, so two results. So far, so good. Maybe some of you tried this one during the break. So, okay. Now, again, let's label these two sets, set A, set B. And, well, let's plot these two sets. All right. So that's A, set A, set B, and in this case we want the union of them, A union with B. All right, so again, let's have the zero in the middle, right? Have the 0 in the middle, and have to have some number sense. So we're going to plot for letter A all the numbers that are less than negative or equal negative 2. And that's going to be represented with brackets this time, pointing towards the left. All right. And let's see, so that's going to be, okay, I'm going to use blue for shading this set. And for set B, that's 1/2. I'm going to represent it like this. 1/2. And have that go to the right. And putting these two sets together like this and like that, that's going to be on this side in pink or red, and towards the left the one in blue. And well, in this case, notice there are no intersections like it could be the case, by the way. All right. So we need to represent the solution, these two shaded intervals using interval notation. All right. So let's see. Let's write this down like negative infinity to negative 2 with a bracket union, open bracket, and that's a 1/2 to positive infinity. And as for the set builder notation, x such that, just write down these two inequalities, x less than or equal negative 2, comma, or separated by commas, x greater than or equal 1/2. All right. So you may need to represent this by commas in the case if you're asked to input the blanks in MATLAB. I'm not sure if it asks for set builder or just the interval notation, but for sure you need to, at least for the paper, for our exams and quizzes, you need to know both of them. And I believe that's about this topic, right?